Welcome to The Communicator, your quick journey into the world of chemical engineering. I'm Amanda Sabrino, AQ Student Development Officer. Whether you're a chemie or just curious, join us as we make chemical engineering exciting and accessible. Time to catalyze some great conversations. Let's go.
Hi, my name is Isabella Villanueva, and I am the Corporate Events Chair for AQ.
Hi, I'm Amanda Sabrino, and I'm the Student Development Chair for AQ, and this is The Communicator. Today, we're here with Dr. Freeman.
And would you like to introduce yourself?
Sure. My name is Freeman. I'm a professor of chemical engineering at University of Texas at Austin.
So you're the director of the MWET for UT Austin. Can you talk a little bit about what you do as the director and what the general goal is of the MWET?
MWET's the Center for Materials for Water and Energy Systems, and we are researching new types of membranes for low energy separations for water purification and resource extraction, like extraction of critical metals like lithium from brine sources. And so we have a number of teams in Austin, Santa Barbara, and Berkeley, California, that are focused on making new materials, characterizing them, and then we do a lot of computer simulation of those materials. My main job as director is to represent the center before our sponsor, the U.S. Department of Energy. We work with the Office of Science of the Department of Energy and Basic Energy Sciences program, which is the most basic science part of the U.S. Department of Energy. And so we're focusing on the basic science questions that prevent progress technologically, prevent engineering progress. My job includes keeping up with our sponsor and what they want, communicating that to the team, making sure we get our reports in on time, helping coordinate the research from 20 faculty and probably 25 or 30 graduate students and postdocs so that we're all working in the same direction, so towards the same goal, and listening to the team to make sure that we've got our work, we understand what the capabilities are of the team and how we can work together to make progress in the so-called water energy nexus for low energy separation membranes.
Cool. So students who are interested in the research you do, what would you recommend, or I don't know, if they have an interest, how would they get started in doing that kind of research?
So the way I got started was in about 1980, when I was a sophomore in chemical engineering. I had a thermodynamics teacher who was really kind, and he was doing membrane-based research, and so the rumor was that he would take undergraduates doing research, and so I went to work in his lab, and that was how I got introduced to membranes. And so one of the ways to get started in this field, if you're in school, is to go to folks who work in an area you're interested in, be it membranes or something else, and talk to the teachers, talk to your teaching assistants, because they're all PhD students in somebody's research group, and they may be able to help you get entrance into a lab experience or understanding more about a given research field.
Well, thank you.
So with you being in membrane research since your sophomore year, what's your favorite part about the field, and what keeps you interested in it?
Well, basically, it's I think it's taking the knowledge that you gain over a long period of time and applying it to new problems and finding out where the things that we take to be the gospel truth based on past experiences, where that works and where it doesn't. And every time we study a new problem or step just outside the boundaries of what has been probed in the past, we're always finding that the rules and the laws that we thought applied to all systems don't quite apply to all systems, and they have to be modified, and so we increase our understanding of how the world around us works.
That's really cool.
I'm gonna veer a little bit. When did you become director of MWET?
On August 1st, 2018.
Okay. So what How has that transition been from what you were doing before to a bigger sort of managerial role? Like, what made you decide to take that on?
There had been talk for a long time about the possibility of the Department of Energy getting involved in water purification. Historically, they've not viewed water treatment as an issue that they had to deal with because they're charged with energy security in the United States. And you may have, if you've lived in Texas, you would have lived through the terrible droughts we had in like 2011, 2012, and remember various aspects of the way that impacted your life. It was causing problems for our energy generation. Power plants that rely on cooling water were having to stop or slow down because they couldn't get enough water to run the power plants. And this is in the middle of summer in Texas. Small towns were running out of water and having to have water trucked in. This was also during the time when hydraulic fracturing, so the energy revolution in the U.S. was taking off. And that process requires several million gallons of water to fracture a well. And so there was a competition between the water being used for agriculture or going for energy production. And so there's a stress between water and energy and food. And it was around this time that the Department of Energy decided that in order to secure energy security for the United States, they had to also be involved in water security. And they set up, as part of that, they set up a broad array of programs in this space, and it ranges all the way from a desalination hub, which is a nationwide applied research and development center, down to very basic science centers like the ones that we have. And so in late 2017, they issued a call for proposals for the types of centers that MWIT is, the so-called Energy Frontier Research Centers. And for the very first time, they issued that call with topics in the water energy nexus and looking for technologies and ways to make energy less water intensive, and also to make water less energy intensive, to break the connection between water and energy. And so this looked like it was the ideal time to get involved in such an effort. It was brand new for the Department of Energy, and it was the right time for me in my career, and it was more or less a calling. And so I got a coalition together of like-minded people, and we applied to the program and were successful.
Awesome. That's a great story.
Yeah. Okay, so kind of going off into another topic, we read that you did your postdoc in France for college, and you also do research about half the year in Australia at Monash University. Could you talk a little bit about like what the differences are in schools in Europe versus Australia versus here, and kind of like any differences in attitudes that you see?
Well, it would, sure. The comparisons I would make would be, they're not just based on geography, they're based on time, because I would have been living in Paris in the late 1980s, and then teaching at Monash as recently as this past November. And so, in the same ways that that attitudes change here over the course of your lifetime, I'm sure there may be things that I would have noticed in Paris, for example, that may not be true today, and vice versa. I went there at a time when that particular laboratory was the more or less the center of the universe for the type of research that I did. And as a young person, it was a remarkable opportunity to meet basically the leaders in the field from around the world, because they would come and give seminars and stay, a week or two or a month. It's not a hard place to stay in Paris. right downtown. And so you get a chance to network with some of the very top people in the field. The director of the center was 2 years after I left, won the Nobel Prize in Physics for his work in the polymer field, which is where I work, the area I work in. So it was absolutely amazing place to be. They were undergoing the first, to consider some contemporaneous topics. They were undergoing their first big grappling of immigration and what that meant, for French society and how they were going to manage that. And some of those questions go on today in France. In Australia, they Australia is quite a different place, being where they are located. Their trading partners are quite different. It's all of the Eastern Pacific Rim countries, and so if you go there, you'll find very good Sri Lankan food and food from Vietnam and Malaysia and Indonesia, and because the people have come and they've brought their culture and their food. Whereas most of the French schools were highly populated with French citizens. The Australian schools, probably more than half the university are people from outside of Australia. So it's students coming from these Pacific Rim countries to get a Western education, and then many of them going back to their home countries. It's viewed as a sort of soft diplomacy to bring people into your culture and to have them experience it and hopefully enjoy it and take some parts of it back with them. This was the mission of Senator Fulbright, who established the Fulbright program, if you're familiar with that. It was to get people talking and working together so that they wouldn't fight. And they really embraced that in Australia. By the same token, we have an exchange program with Monash where you can go and spend a semester abroad and take chemical engineering courses using the same textbooks that you use here on the 40 acres, and have those courses count back towards your degree here. So if you're ever interested in seeing penguins and kangaroos and things of that nature, there's a way to do that, and the door is open, I would say.
I've heard that kangaroos are terrifying.
Well,
they're really muscular from what I've seen.
They come in all different sizes. From ones that would easily fit on the tabletop to ones that you'd avoid. You'd want a fence between you and them.
Yeah.
That's a lot.
Oh my gosh.
That's a lot.
They scare me.
They do scare me too. I saw a video of a kangaroo picking up a guy's dog and taking it.
Oh, right, okay.
Yeah, something to consider next time you're there.
Well, the good news is they're not just bouncing around all over the place on the Monash University campus.
That's good.
You normally have to go someplace to see them, in the same ways. In some parts of Texas, you'll have animal or cattle crossing signs on the roads, and so in Australia you'll have you'll have kangaroo crossing signs. You have to, or deer in this part of Texas. You have to be careful about them crossing the roads. You'll have that with in Australia. There'll be signs that they're maybe crossing the road, so you have to be careful of them.
That's awesome. That's really funny. Okay, and then we're kind of going to go back to academics. It's kind of an odd order. But since you've been teaching at the university for so long, have you noticed, or is there anything you want to talk about, like big changes in the department specifically?
Well, at least in chemical engineering, when I started, the U.S. was just coming out of the Arab oil embargo, and there was a gold rush for chemical engineers in the chemical industry, so every graduate had 2 or 3 job offers at least. There weren't enough chemical engineers at the time, Now, eventually, the supply and demand worked itself out, but the curriculum was, you would recognize many of the courses. I presume you've gotten through CHE 317?
I'm in it right now.
Yeah, all of us are freshmen.
Okay.
Yep.
Well, so a lot of the courses would look very much the same because we're teaching the fundamentals of the field. There were courses that I took that you probably wouldn't take today. It was required of all engineers to take mechanical drafting, drawing by hand, like plans for, plants or the things that you'll do on a computer now. We had to learn to do by hand. So you won't find mechanical drafting courses in your curriculum. We took electrical engineering courses because the idea was that if you're going to be a chemical engineer, you had to know how pump motors worked, among other things. And nowadays, I think those courses have been replaced by like bioengineering, some of the more modern aspects of the field. The places where chemical engineers went to work were largely in the chemicals industry, oil and gas industry, and things like that. Today, the opportunities are much, much broader. We send people in the semiconductor business. The types of chemicals that, if you go into the chemicals industry, that we make and things that we do are, would not have been imaginable when I started my career. So, for example, you all have computers and phones and cameras that run on lithium-ion batteries. When I started, the rechargeable lithium-ion battery hadn't been invented, and so there was no need for things like lithium extraction, to make lithium-ion batteries because they didn't exist. And so areas where we would work in research, for example, a lot of those areas didn't exist. The biotech revolution, with gene editing and things like this, was really has come on in your lifetime, and so that has changed some of the topics that we address. The types of faculty that we hire today, because the field is so much broader, is going beyond just traditional chemical engineers to people who have specialties in microelectronics and in bioengineering, and now we're looking for specialists in AI related to chemical engineering, which was not even on the radar screen 40 years ago. So the field, we still teach the traditional subjects in chemical engineering because a lot of our graduates go in that direction or go in the direction where those skills are valuable. But we're also teaching a lot more in some of the new areas where opportunities are coming up for chemical engineers.
Cool.
So going back to earlier when we had asked you what made you want to stay in membrane research for such a long time, and you mentioned that there are a lot of things that you uncovered that you thought were true and they're not true. Do you have like a favorite big discovery that you've had?
So there are several. I had told one of my team members came to me and found this really interesting article in a journal about coating a particular substance, which in the literature is called polydopamine, onto surfaces, and this material would coat about any surface, and it made the surface hydrophilic. And he said, I think this would be interesting to put on membranes because it would make them fouling resistant. If you're filtering dirty water with the membrane, the filter gets dirty. And you'd like to have filters that are self-cleaning, like your pots and pans. Mm-hmm. And one of the keys to that is that many of the things that cause, that will stick to it, the membranes are all hydrophobic so that they don't dissolve in water when you're using them. Many of the things that would stick to them are also hydrophobic. If you think about, emulsified oil droplets in oil, in water rather, if they come across a nice hydrophobic surface like a membrane, they're going to stick to it to eliminate some of their interactions with water. And so my students thought, well, if we could make just the top 10 nanometers of the membrane hydrophilic, maybe we could get it to be less likely to attract those kind of foulants or contaminants in water. And I told them they could give it a try, but it was unlikely to work, because I can always think of a dozen reasons why something won't work. And they gave it a try, and in fact it worked better than anything else we were doing at the time. And I completely changed that part of my research program towards that area. And those membranes were ultimately, we published a lot of papers on them and licensed the patents that we had in that space. And so they're made today by a company in Chicago. You can go buy them. And so, that was one example. Another example was we were trying to make membranes that were more permeable to carbon dioxide than to hydrogen. And you may or may not remember the era of clean coal. In the early 2000s, about the time of the George W. Bush administration, we were running out of oil, if you can believe that, if you can remember that time. And there was concern that we wouldn't be able to get access to the energy we needed to run the country. And people still remember the oil shocks in the 1970s and long gas lines and the economic pain that had brought. And so there's a big effort to undertake converting coal to hydrogen. And the U.S. has enormous amounts of coal, and it was called a clean coal program. And we were going to take coal and put it through the water-gas shift reaction to make CO2 and hydrogen. And the hydrogen would then be burned in turbines or used in fuel cells to generate energy. And CO2 at that time was a harmless gas and would be released in the atmosphere. So they're looking for technologies to separate CO2 from hydrogen. And I worked for a long time with a team of researchers, and we found membranes that kind of worked the opposite of existing membranes that had really good separation properties for CO2 over hydrogen. And they worked the opposite of traditional membranes because they allowed the CO2 to go through preferentially over the hydrogen. Normally membranes permeate the small molecule, not the large molecule preferentially, and these were reverse selective. And we worked and designed them that way. And then around 2008, the shale gas revolution came, and politics changed. We no longer needed clean coal because we had plenty of oil and gas. And in the Obama administration, CO2 went from a harmless gas to a pollutant. And research turned towards carbon capture. And it turns out that if you have membranes that can separate CO2 from hydrogen really well, they're outstanding at separating CO2 from nitrogen, which is the dominant separation in carbon capture from thermoelectric power plants. And so today, those membranes are used for that purpose in demonstration facilities, the largest of them being a facility that Exxon and the Department of Energy are partnering with out in Wyoming, and they're going to use millions of square meters of our membranes for that. They're made by a company in California called Membrane Technology and Research. They're the Polaris membranes. Polaris because they separate polar or quadrupolar compounds like CO2 out of gas mixtures. But those are a couple examples where we found things that were against the grain of what was supposed to happen in separations. More recently, I was working with colleagues at Monash University, and they were showing me results on separation properties that had very unusual separation characteristics for taking lithium ions out of mixtures with other salts. And I encouraged them to patent that. That work came to the attention of an investigator, of an investor here in the U.S. who was looking to start a lithium extraction company. And so he licensed our patents and went on to start a company here in Austin called EnergyX. They have about 100 employees now, and they're building lithium extraction technologies based on a number of approaches. And so that's been another area where, you know, a laboratory curiosity kind of started the ball rolling towards something that now is a pretty big concern and employs a bunch of Longhorns, actually. You know, we have several of your colleagues that are a little further along who have joined the team at EnergyX. They're up near the Domain.
Oh, that's so close.
Yeah.
I didn't know membranes could be used for so many different things. It's really interesting.
This has nothing to do with engineering, but as you've been talking about a lot about politics and different areas in the field, and this kind of has something to do with it, but do you have, actually it doesn't really, it just got me thinking, do you have like a favorite book or a favorite movie?
Yeah, I can't think of one. I mean, I love a lot of movies, and I've read a lot. I don't read as much as I used to, nonfiction work, because the torrent of keeping up with scientific literature there are just a lot more articles published today than when I started my career. I probably by a factor of 10. And the field has grown in interest worldwide to where that's just about all I can keep up with right now. I look forward to, at some point in the future, getting back to reading for fun.
Yes.
But right now it's just trying to keep my head above water and make sure trying to understand what's going on in the field.
Yeah. Okay. Have any other questions?
How did you get involved with Monash University, and what made you want to start teaching over there?
So they had capability that we did not have in experimental characterization tools, and in fact that at the time virtually no one had in the world. And this is basically using so-called positron annihilation experiments to study the interior structure of materials. And so you may have heard of a positron. It's a positively charged electron, antimatter. And so you can create these out of a number of ways, but they can be created naturally out of certain isotopes of, say, sodium, or you can create them in a synchrotron, like at a national laboratory facility. And if you inject them into material, a positron and an electron will combine, and they will annihilate one another, according to Einstein's formula, E equals mc squared. And when they annihilate, they release a flash of light. And how long they live inside a material in nanoseconds tells you how big the cavity is that they're exploring. And a lot of the properties of how molecules move through membranes depends on how big is the space they're going through. And so the positrons can help map that space out. And they had this capability at Monash University. I began collaborating with scientists there in about 1995, and we published our first paper in 1997. Let's see, that's how many years ago? To work together, I sent students there, their students came here, and we publish now, I think, upwards of about 50 papers or so. And as I and I was thinking about it, particularly as we started to come out of the pandemic, about how important it had been for my career to have gotten off the farm and gotten to travel, and how it changed my life forever. And I thought about how could you set something up to help the next generation of students have access to that, and to get out on the road early and see what it's like to live in a different part of the world, and to experience a different culture. And so when I thought about where to do that, most of our students, many of our students at Texas, actually speak more than one language, but by far English is the most common. And of the English-speaking countries, you could imagine going to Great Britain, and we already have a number of exchange programs there. We had far fewer in Australia, and it's further away, and I thought, well, it seems more exotic. And as a parent, I thought, well, I would only want to send my child to a place not only where they could get a good education, get access to a different culture, but it needed to be safe, and it needed to have a good healthcare system. And Australia, and it needed to be a place where they were this society was ordered by the rule of law. That it's not arbitrary what happens to people as they're walking down the street. And Australia ticks all of those boxes. And so, and the university here, at about that same time, hired their first ever vice provost for global impact. And UT said, we want to be a global university, we want to have global impact. And so there's an ascendancy inside the university of trying to create channels to have global impact. And the University of Monash was very open to having a relationship with the University of Texas. Monash is the #1 chemical engineering department in Australia. And so, UT would not partner with places that are not excellent. And so that box was ticked as well. And so this is how we came to set up the exchange agreement. For me, it's about paying it forward. Some of the many benefits that I got from experiences traveling around the world, to put in place programs so that others could get started. Because when you go to a country like Australia, and they more or less speak English, you can understand them, but then some of the words are different, attitudes are different, and then you get a whole different perspective on your own culture as an American when you see it from outside. And I just think one of the things that we at Texas should be doing is educating global citizens, global engineers. You may well find yourself working in teams that literally span the globe, and understanding differences in culture of people and how they work can really help you make a much bigger impact. I have a personal story about that. My wife and I have one son. He graduated chemical engineering, I'm sorry, from A&M, and works for an engineering company called Fluor in Houston. And so they, if you want a chemical plant, Fluor will design it for you, and they'll get somebody to build it for you. So they're that sort of engineering company. And they have my son's on a team where they're building a propane cracker for Saudi Aramco out in the desert in Saudi Arabia, so to convert propane to propylene. Samsung is also a partner, Samsung Engineering, in South Korea. And so he goes in at 7 a.m. in the morning to have video calls with their team members in Saudi Arabia, because they're ahead of them. And then late in the afternoon, they can get on with the Korean colleagues who are just coming to work the next day with the time difference. And he'll leave this Saturday on his very first business trip, going to Seoul for 2 weeks.
Oh, that's so cool.
as
That
part
is
of
very
it.
exciting.
But this is what engineering means today. You know, you're not going and working in an isolated place and by yourself. There's a lot of these jobs where you're working in global teams, and so your work goes, in 24 hours goes around the world, and other people have to act on it. And so understanding how to interface with people from different cultures and different time zones and things like this, I just think is really critically important. And if you've been there and lived in these places, you'll have a much better appreciation of it.
Yeah.
I think that's some really great advice, and I also think that might be all the time that we have for today. Thank you so much for
You're
Yes,
welcome.
this has been wonderful.
Yeah, we had a great time talking to you.
Well, likewise.
Thank you for listening to The Communicator. If you'd like to learn more about UT's Chemical Engineering Department, then check out our other episodes. We hope to see you again. Same time, same place, different reaction.